Electrical grounding is a critical aspect of electrical systems, primarily implemented for safety. It establishes a low-impedance path for fault current to return to the source, enabling overcurrent protection devices like circuit breakers to quickly interrupt the circuit and prevent electrical shock or fire hazards. Grounding serves several essential functions. Firstly, it protects individuals from electrical shock by providing a safe path for fault current, minimizing the voltage potential between conductive surfaces and ground. Secondly, it safeguards electrical equipment from damage by limiting the duration and magnitude of fault currents. Thirdly, it reduces electrical noise and interference, improving the performance and reliability of electronic devices. There are primarily two types of grounding systems. Firstly, system grounding, which connects the neutral point of the electrical supply transformer to earth, and secondly, equipment grounding, which connects non-current carrying metal parts of electrical equipment to ground. System grounding stabilizes the voltage of the electrical system and provides a reference point for overcurrent protection. Equipment grounding ensures that metal enclosures, conduit, and other conductive parts are at or near ground potential, minimizing the risk of electric shock if a fault occurs. The grounding electrode system is a network of interconnected grounding electrodes that provide a reliable connection to earth. Common grounding electrodes include ground rods, ground plates, metal underground water pipes, and concrete-encased electrodes, also known as UFA grounds. The National Electrical Code (NEC) specifies the requirements for grounding electrode systems, including the type, size, and number of electrodes. Ground rods are typically copper or copper-clad steel rods driven into the earth. Ground plates are metal plates buried in the ground. Metal underground water pipes can be used as grounding electrodes if they meet certain requirements. Concrete-encased electrodes are reinforcing steel bars or bare copper conductors encased in concrete foundations or footings. The grounding conductor is a conductor used to connect equipment or the grounded circuit of a wiring system to a grounding electrode or electrodes. Grounding conductors can be either bare or insulated. The size of the grounding conductor is determined by the size of the circuit conductors, as specified in the NEC Table 250.122. The equipment grounding conductor (EG) is the conductor used to connect the non-current carrying metal parts of equipment, raceways, and other enclosures to the system grounding electrode conductor at the service equipment or the source of a separately derived system. The EGC provides a low-impedance path for fault current to return to the source, enabling overcurrent protection devices to operate. The ground fault circuit interrupter (GFCI) is a device that protects people from electrical shock by monitoring the current balance between the hot and neutral conductors. If there is a difference in current, indicating a leakage to ground, the GFCI quickly interrupts the circuit. GFCIs are required in wet locations such as bathrooms, kitchens, and outdoor areas. They are also recommended for use in areas where electrical equipment may come into contact with water. Bonding is the process of connecting together all metal parts of an electrical system to create a low-impedance path for fault current. Bonding helps to equalize the voltage potential between different metal parts, reducing the risk of electric shock. Bonding also helps to reduce electrical noise and interference. The main bonding jumper is the connection between the grounded circuit conductor and the equipment grounding conductor at the service equipment. The equipment bonding jumper is the connection between two or more portions of the equipment grounding conductor. Grounding and bonding are essential for electrical safety. Improper grounding or bonding can increase the risk of electric shock, fire, and equipment damage. Regular inspections and testing of grounding systems are necessary to ensure their effectiveness. When performing electrical work, always follow the requirements of the NEC and local electrical codes. Always use appropriate personal protective equipment, PPE, such as insulated gloves and safety glasses. To energize circuits before working on them whenever possible. Use a voltage tester to verify that circuits are de-energized. Never work on live electrical equipment unless absolutely necessary and only when qualified and trained to do so. Effective grounding is achieved by minimizing impedance in the ground fault path. Low impedance ensures that fault currents are high enough to quickly trip over current protection devices. High impedance can limit fault currents, delaying or preventing the operation of circuit breakers, increasing the risk of electrical hazards. Impedance is affected by conductor size, length, and material, as well as the quality of connections. The NEC provides specific requirements for grounding different types of electrical systems, including alternating current (AC) systems, direct current (DC) systems, and separately derived systems. Separately derived systems, such as generators and transformers, require their own grounding electrode systems. The NEC also addresses grounding requirements for specific types of equipment, such as motors, transformers, and electronic equipment. Ground testing is a method used to verify the effectiveness of a grounding system. Ground testing involves measuring the resistance of the grounding electrode system to earth. A low resistance indicates a good connection to ground. A high resistance indicates a poor connection to ground, which may require further investigation and correction. Common ground testing methods include the 3-point fall of potential method and the clamp-on ground resistance meter method. The 3-point fall of potential method involves driving 2 auxiliary ground rods into the earth and measuring the voltage drop between the grounding electrode and the auxiliary ground rods. The clamp-on ground resistance meter method uses a clamp-on meter to measure the current flowing through the grounding conductor. Grounding systems should be inspected and tested regularly to ensure their effectiveness. Inspections should include visual checks of grounding conductors, connections, and grounding electrodes. Testing should include measurements of ground resistance and continuity. Any deficiencies identified during inspections or testing should be corrected promptly. The size of grounding conductors is crucial for ensuring adequate fault current capacity. The NEC specifies the minimum size of grounding conductors based on the size of the circuit conductors. Undersized grounding conductors can limit fault currents, delaying the operation of overcurrent protection devices and increasing the risk of electrical hazards. The material of grounding conductors also affects their performance. Copper is the most common material used for grounding conductors due to its high conductivity and corrosion resistance. Aluminum can also be used for grounding conductors, but it must be sized larger than copper conductors to provide equivalent performance. Connections in grounding systems must be properly made to ensure lower impedance and reliable performance. Connections should be clean, tight, and corrosion resistant. Common types of grounding connections include bolted connections, compression connections, and exothermic welds. Exothermic welding is a process that creates a permanent, molecular bond between two metal conductors. Grounding electrodes should be located in areas with low soil resistivity. Soil resistivity is a measure of the resistance of the soil to the flow of electrical current. Low soil resistivity allows for better current dissipation and lower ground resistance. Soil resistivity can be affected by factors such as moisture content, temperature, and mineral content. The NEC requires that grounding systems be installed in accordance with the manufacturer's instructions. The manufacturer's instructions provide specific guidance on the proper installation and maintenance of grounding equipment. Following the manufacturer's instructions helps to ensure that the grounding system is installed correctly and will perform as intended. Grounding systems must be protected from physical damage. Grounding conductors and electrodes should be located in areas where they are not likely to be damaged by vehicles, equipment, or other objects. If grounding conductors are exposed to physical damage, they should be protected by conduit or other means. Grounding systems should be designed to minimize the risk of ground loops. Ground loops occur when there are multiple paths to ground, creating a circulating current. Ground loops can cause electrical noise and interference. To minimize the risk of ground loops, grounding systems should be designed with a single-point ground. The NEC provides specific requirements for grounding sensitive electronic equipment. Sensitive electronic equipment, such as computers and communication equipment, can be susceptible to electrical noise and interference. To protect sensitive electronic equipment, the NEC requires that it be grounded using a dedicated grounding conductor. Grounding systems should be designed to accommodate future expansion. As electrical systems are expanded, the grounding system should be upgraded to ensure that it continues to provide adequate protection. The NEC requires that grounding systems be designed with sufficient capacity to accommodate future loads. Grounding systems should be documented to provide a record of the grounding system design and installation. Documentation should include drawings, specifications, and test reports. Documentation should be kept up to date to reflect any changes to the grounding system. Grounding systems play a crucial role in protecting people and equipment from electrical hazards. Proper grounding practices are essential for ensuring electrical safety. By understanding the principles of electrical grounding and following the requirements of the NEC, electrical professionals can design and install safe and reliable grounding systems. Maintaining a grounding system involves routine checks and upkeep to ensure its effectiveness. Firstly, visually inspect all grounding conductors and connections for corrosion, damage, or looseness. Secondly, tighten any loose connections and replace any damaged components immediately. Thirdly, perform ground resistance testing regularly, ideally annually, using appropriate test equipment. Fourthly, check for any modifications or additions to the electrical system that might require adjustments to the grounding system. Fifthly, keep records of all inspections, tests, and maintenance activities for future reference. By adhering to these steps, you can maintain a safe and reliable grounding system, preventing potential electrical hazards. When it comes to electrical safety, understanding grounding is paramount. For instance, a common misconception is that grounding only protects equipment. While it does protect equipment from damage due to overvoltage or fault currents, its primary purpose is to protect people from electrical shock. Another area of confusion is the difference between grounding and bonding. Grounding provides a path for fault current to return to the source, while bonding ensures that all metal parts are at the same electrical potential, minimizing the risk of shock if someone touches two different metal parts. Also, many believe that a GFCI replaces the need for proper grounding, but a GFCI provides additional protection by detecting small leakage currents that may not be sufficient to trip a circuit breaker. However, it still relies on a properly grounded system to function effectively. Grounding and bonding work together to provide comprehensive electrical safety, ensuring that both people and equipment are protected from electrical hazards.